our points should work in the equation. So I'm just going to choose the point 1 comma 1600. Okay, so I choose that point. So A is 1600 and T is 1. Okay, so T is 1. And does that work? Well, 1600 equals 1600, so that works. And then I just chose another point, 4 comma 1000. So when T is 4, okay, so time is 4 and A is 1000. Does that work? Well, the answer is yes. Okay, next example. Okay, this is an example we actually come back to a few times in this course, so this is a good one to look at. Okay, R is the death rate, the number of deaths per 100,000 people from heart disease in the U.S. for the year that is T years since 1960. Okay, now you gotta be careful on this when you look at understanding what this means. In the year 1960, the death rate was 559. So you have to think about, what does that mean? Well, the year 1960, that's pretty obvious. But the death rate of 559, what that means is, it's the death rate, the number of deaths per 100,000 people from heart disease. So 559 would mean that there were 559 deaths per every 100,000 people. Now what that means is, if the population, so just suppose the U.S. had a population of 100,000 people in 1960, you would have expected 559 deaths due to heart disease. If there were, say, 200,000 people in the population, now I know this is not accurate, but just kind of building an idea of what this actually means. If there were 200,000 people, that's twice 100,000. Okay, so if there were 200,000 people in the entire U.S., you would expect 559 times 2, okay, or about 1,100 people to die due to heart disease. If there were 1 million people in the population in the U.S., so that's 10 times 100,000. So if there were 1 million people in the population in 1960, we would expect 5,590, which is 559 times 10. So we'd expect 5,590 people to die due to heart disease in 1960. Okay, so the reason they use that number of deaths per 100,000 people is because the population is constantly changing. So it wouldn't be a good way to look at it as just the number of deaths in the U.S., because the number of deaths may be going up due to heart disease, but there's also more people as time goes on. Okay, so just to look at the number of deaths would be a very tricky way of reporting looking at the deaths due to heart disease. Okay, so that per 100,000 people, it means you can make comparisons from one year to another, or even like cross country, or across different countries, or across the world. Okay, so that per 100,000 people allows you to make valid comparisons. Okay, so like maybe you look at, say, China. Like China may have 20 million people die due to heart disease in a certain year, which that may be a lot more than in the U.S. as far as the numbers of people that die due to heart disease, but the rate may actually be smaller because they have so many more people than the U.S. does. I think they have over 1 billion people. Okay, so again, that per 100,000 people allows you to make comparisons. Okay, so to create a scattergram, okay, same idea. The year since 1960, that's pretty standard. We have 1960, 70, 80, 90, and so on. So the t-values will be 0, 10, 20, 30, 40, and then 48. Now, don't let that throw you off. We'll just estimate where 2008 is. Okay, don't make that change your scale at all. We'll go up by tens and don't change the scale because of that 2008. And then the death rate, 559, then 493. It looks like it pretty much decreases down to 187. But again, it's decreasing, so we may be interested in at what point does it actually reach 0. So we're going to fit positive t and r values on our axes. So that means we're going to put our axes in the bottom left again. Okay, and again, mine is all done just to save time. I decided to go up by tens for every other tick mark. which means every tick mark is 5, even though they're not actually on the grid here, or in the table, just to space it out nicely. So every other tick mark is 10, so 0, 10, 20, and so on. And then up the side, this takes a little bit of, guesswork or figuring out. But if I fit from 0 to say about 600, okay, then a scale of 50 works pretty good. And again, that's something that if you want to pause the video or stop and try to figure it on your own, please do that. I will expect you to be able to do this when I grade anything to make a valid scale. Okay, so we have the year since 1960 across the bottom, the death rate per 100,000 people going up the side, and plot the points, and that is your scattergram. The line is not part of your scattergram. Part A are the points without the line drawn. But in part B, I tell you to draw a linear model. So is the data linear or approximately linear? Well, again, it has the idea of if you were to try to draw a line through 2 points, remember these points were not really nice to graph or plot. Okay, but notice what I have here. If I try the last 2 points, notice that that line is not going through all the points. Okay, so it's not exactly linear. So we're going to say approximately linear. I drew a linear model in there. Okay, so that linear model is the best one I could draw. When you draw yours, the idea is you want to have a line that is close to the points. What you don't want to do is you wouldn't want to draw a line where all the points are under the line or all the points are over the line. You want to draw a line that's kind of like passing through the points. Okay, so notice how on mine, I have a couple points that are below the line, a couple that are above. One looks like it's on it or very close, or a couple of them do. Okay, so you want to draw a linear model that's through the points or close to the points. Okay, not all above or all below the points. Okay, moving along now. What is the t-intercept of your model? Okay, so t-intercept, what that means is where does our model, so where does the line that we drew, intercept the t-axis? So it looks like right about here. So that would be, well, here we have 60, 65, 70. So I would say right around 67, comma 0. And to explain the meaning of that point, we'll remember that t, the first value in your ordered pair, is the number of years since 1960. So, oops, I'm sorry, I have the wrong number there. So 67 years past 1960. That would be the year 2027. Okay, that's 2027. We would expect or predict the death rate to be 0 deaths per 100,000 people. Okay, so right here, representing the year 2027, we would expect the 0 death rate. So 0 deaths per 100,000 people. Okay, the r-intercept of our model. Well, the r-intercept is where does our line that we drew intersect the r-axis. Well, notice how it's above the point that I have drawn. And this goes back to a previous concept of we don't even care what the value in the table was. So pretend we don't even know what the value in the table is. We're trying to find the r-intercept of our model. Our model is the actual line that we drew. So I would say, based on mine, it looks like it's about halfway between these two tick marks. So this is 500, 550, and then 600. So halfway between 550 and 600 is about 575. So I said 0, 575. And to interpret that meaning, in 1960, we would predict the death rate to be 575 deaths per 100,000 people. Now again, that's a prediction because that's using our model. Okay, so that word there is actually important to say predict. Okay, and then lastly in part E, use our model to predict the death rate in 2015. Okay, and then in 2015, that is a t-value of 55. Okay, and one way to get that is to do 2015 minus 1960. That gives you a t-value of 55. And it looks like on my grid, it's right about 100. Okay, right around 100 for the death rate. Okay, so the death rate, when t is 55, we get about 100. Okay, so that's 100 deaths per 100,000 people. So there's the death rate. Okay, and then it goes on to ask us if the population will be approximately 320 million in 2015, then how many Americans will die of heart disease in 2015? So we know for every 100,000 people, there's going to be 100 deaths. We want to know how many deaths would there be if there were 320 million people. There is more than one way to find the answer to this. Okay, and again, I suggest you take a minute and think about it, but I'm going to keep talking, okay, because that's what I like to do. Okay, no, it's just for the sake of time. We're getting long here. Okay, so pause the video and think about how would you actually find that, the number of Americans that would die due to heart disease in 2015. Okay, so one way to look at it is the number of deaths would be the death rate times the population. So if we know that there's 100 deaths for every 100,000 people, if you multiply that by 320 million people, that'll give you the number of deaths. Okay, so that's one way to find the answer. Okay, 320,000 deaths. Okay, another way to find the answer would be to set up a proportion. Okay, and remember anything about proportions, the way they work is you take the ratio that you know. We know that there is 100 deaths per 100,000 people. Okay, so that's the ratio that we know. We can take that ratio and set it equal to, if there's 100 deaths per 100,000 people, then how many deaths per 320 million. So there you cross multiply 320 million times 100 and then divide by 100,000. Okay, so you would do 320 million times 100 and then divided by 100,000. Okay, it gives you 320,000. Okay, so those are examples of drawing scattergrams and approximate linear models. Okay, and we use our linear model to make predictions. Okay, so hopefully that's enough for you to feel comfortable with drawing scattergrams and working with linear models. Okay, the idea of the equations of linear models, okay, like well, I misplaced my page here. Okay, but trying to find the equation of linear models, that's something that we build on throughout the course. Okay, so don't get too stressed out if you're having a little bit of trouble with the word problems in finding the equation of the linear model.